In today's video, we will see how we can improve the time response of a system. So it is necessary for a control system to meet certain specification regarding its performance. So in addition to the control system which we have, we can add some more into it so that we can change the design so that we can obtain a better response. So we add a controller to it. So a controller is a device when it is introduced. It can be either introduced in the feedback path or in the forward path. It will improve the steady state and the transient response of a system. It will control the response of the system. So the type of controllers which is used either in the feedback path or forward path are proportional control, proportional derivative control, proportional integral control, proportional integral derivative control. PD, PI and PID control. So we will study about each of the controllers in detail. The proportional controller. So it is a device that produces a control signal. Control signal here is U of S, which is proportional to the input error signal, which is E of S. So E of S is R of S minus the feedback signal. So U of S is proportional to the error signal, which is E of S. So we have U of T proportional to E of T, which is the error signal. It is equal to Kp. It is the proportionality constant Kp into E of T. If we write it in Laplace domain, it is U of S is equal to Kp into E of S, or Kp is equal to U of S by E of S. So the proportional controller, that is the P controller, amplifies the error signal by an amount Kp. So U of S is the control signal. The error signal E of S is amplified by Kp, which gives us U of S. Also, the introduction of P controller in the system increases the forward path gain by an amount which is Kp. So if we write C of S by E of S, it is Kp into G of S. So your forward path gain is also increased by Kp. So if the forward path gain is increased, then the peak overshoot increases. So if the forward path is increased, the first thing is the peak overshoot increases. Second point is the steady state error is reduced. Steady state error is reduced. So we have to select Kp in such a way that the peak overshoot and the steady state errors are within the specified values. So in practice, if this forward path gain is increased, sometimes the system becomes unstable. So instead of going for just proportional controller, we go for either PD controller, PI controller or PID controller. The next is proportional derivative controller. As you can see the block diagram over here, we have the forward path function G of S. Along with it, we have the proportional controller Kp and the derivative controller, which is S into Kd. So it can be actually written like this. Here is G of S. Here you have a summer. This is the error E of S. Here you add a block which is Kp, and here you have a block which is Kd into S derivative. These two are given to the sum block. this is U of S, this is G of S, C of S. It can be written this way also. So now the control signal U of T is equal to Kp into E of T plus Kd into dE of T by dt. That means its derivative. So U of S can be written as Kp plus Kds into E of S, or U of S by E of S is Kp plus Kd into S. Now we need what is C of S by E of S. So what is C of S by E of S? It is Kp plus Kd into S into G of S. Kp plus Kd into S into G of S. So G of S, if we consider a second order system, then say we have C of S by E of S is equal to Kp plus Kd into S into G of S. We consider G of S as a second order system with the transfer function omega n square divided by S square plus 2 zeta omega n into S. Now substitute it here. So we get Kp plus S into Kd into omega n square divided by S square plus 2 zeta omega n into S. So from the block diagram it is clear that H of S is 1. So we write H of S is 1. This is C of S by E of S. So now this C of S by E of S is our new block. So this combined together gives us the forward path. So our closed loop transfer function will become C of S by R of S is equal to our new forward path function G of S divided by 1 plus G of S H of S. And do remember, our G of S is not just simply omega n square by S square plus 2 zeta omega n S. It is along with the controller. So our G of S is Kp plus new G of S is Kp plus S into Kd into omega n square divided by S square plus 2 zeta omega n into S, the whole divided by 1 plus Kp plus S Kd into omega n square divided by S square plus 2 zeta omega n into S into 1. 1 is H of S. So now we simplify and get a standard function. C of S by R of S. On simplifying we get Kp plus S into Kd into omega n square divided by S square plus 2 zeta omega n plus Kd into omega n square into S plus omega n square Kp. This is what we get. So the characteristic equation is nothing but this denominator equated to 0. So now this denominator is compared with the standard second order system. Standard second order system is S square plus 2 zeta omega ns plus omega n square equal to 0. So if we compare, say, this denominator, if I take it as equation 1 and this standard one if I take it as equation 2, I have to compare equation 1 and equation 2. So what I get is 2 zeta omega n plus Kd into omega n square, which is this term. is equal to this one 2 zeta is, since in this equation also it is zeta, I use it as zeta dash, 2 zeta dash omega n, or I get, if I further simplify this one left hand side, I get zeta dash is equal to zeta plus half kd omega n. That means the damping has increased. Damping is now not just zeta plus, but it is plus half kd into omega n. So if you use a proportional derivative controller, the effective damping will increase. This will make the system response very slower with less overshoots but increasing delaying time. So if you use PD controller, the time response will have less overshoot but delay time will be more, and it will not affect the steady state error of the system. Next is proportional plus integral control, that is proportional integral controller. Here the error control signal U of S is proportional to the error signal as well as integral of the error signal. So U of t is equal to Kp E of t plus Ki integral E of t dt, where Kp is the proportional control, Ki is the integral control constants. So U of S, we get it as Kp plus Ki by S into E of S by applying Laplace, or U of S by E of S is this. So now our new forward path transfer function, new G of S, is given by the actual G of S into Kp plus Ki by S into our old G of S. So here, if we consider G of S again as the second order function, then we have Kp plus Ki by S into omega n square divided by S square plus 2 zeta omega n into S. This is what we will have. Now we can write the closed loop transfer function. So our closed loop transfer function is C of S by R of S is G of S divided by 1 plus G of S into H of S. So this can be written as omega n square into Kp plus Ki by S divided by S square plus 2 zeta omega n into S, the whole divided by 1 plus omega n square divided by S square plus 2 zeta omega n into S into Kp plus Ki by S into 1. 1 is H of S. So if we simplify this, we get C of S by R of S as Kp into S plus Ki into omega n square divided by S cube plus 2 zeta omega n S square plus Kp S into omega n square plus Ki omega n square. Now if you look, our denominator is, which is the characteristic equation, the power of S is 3. That means it is a third order equation. So thus we have our second order system being changed to a third order system when we add a integral control in the system. So proportional integral control, if we add to a existing system, we get a third order system. So therefore the effect of PI controller on the system performance is, it increases the system order by 1, which will result in the reduction of the steady state error, and the system becomes relatively less stable, and therefore we have to select Ki. This Ki, we have to select it such a way that it has to maintain the stability of the system. So we will combine proportional controller, our integral control action plus the derivative control action to obtain a new action, which is PID controller action. So the combined action of each single one will have the advantage of each of the three individual control actions. So our last controller is proportional integral derivative control. So if we have the proportionality, we have the integral, we have the derivative controller clubbed together, which will give us a PID controller. So our control signal U of S is equal to Kp plus Ki by S plus Kd into S. So the proportional controller, it will stabilize the gain, but it produces a steady state error. The integral controller, it reduces or it completely eliminates the steady state error. The derivative controller reduces the rate of change of error. So the main advantage of having a PID controller is higher stability with no offset and with reduced overshoot. So these controllers are commonly used in process control industries. So again we obtain the expression for C of S by R of S by taking this G of S as omega n square by S square plus 2 zeta omega n into S. So we can write it as C of S by R of S is equal to G of S divided by 1 plus G of S into H of S, where our new G of S is omega n square divided by S square plus 2 zeta omega n into S into Kp plus Ki by S plus Kd into S divided by 1 plus omega n square divided by S square plus 2 zeta omega n into S into Kp plus Ki by S plus S into Kd into 1. 1 means H of S. So we get, on simplifying, C of S by R of S is equal to omega n square into Kd S square plus Kp into S plus Ki divided by S cube plus 2 zeta omega n plus Kd into omega n square into S square plus Kp omega n square into S plus Ki omega n square. So this is what the closed loop transfer function is given with PID controller. So this is again a third order system. So it will reduce the overshoot with no offset and it gives you a higher stability. Hope this controller is clear. Thank you for watching this video.